Picture this. You live on an island with a single hospital, a single runway, and one electrical grid keeping everything alive. Now picture a Category 4 typhoon bearing down on you and there is no road out. No highway leading inland. No neighboring state to drive to. That is not a scenario from a disaster movie. That is the reality facing Guam right now. 170,000 people. Nowhere to go. But Typhoon Sinlaku is only the headline. Behind it, something far more unsettling is taking shape. A simultaneous breakdown across the entire continental United States. Tornado outbreaks. Mountain blizzards. Flash flooding. Geomagnetic interference. All of it unfolding inside a single 72-hour window. And this is the third time in 11 days this has happened. Most people watching the news tonight have absolutely no idea this convergence is even possible. Typhoon Mawar left $3.3 billion in wreckage just 3 years ago. But something about right now feels fundamentally different. This time we are watching a collision of disasters so perfectly timed, so geographically spread, that it may force us to rethink everything we thought we understood about how catastrophe works. If this kind of real-time analysis matters to you, hit like and subscribe, because what is unfolding in the next 72 hours is going to demand every update we can give. Drop a comment telling us where you are watching from and whether you have ever been through a typhoon or a compound weather event. Your experience is part of this story. Now let's get into it. Right now, somewhere in the western Pacific Ocean, a typhoon is organizing itself with deliberate, methodical violence. Typhoon Sinlaku, currently a Category 1 system, sustained winds at 90 miles per hour, is grinding northwest at just 5 miles per hour through Chuuk State, still roughly 800 miles from Guam. It is still feeding, still tightening. And here is the detail that is keeping every meteorologist in the Pacific Basin staring at their screens past midnight. That speed, 5 miles per hour. That is not a storm sprinting through a region and leaving. That is a storm walking, deliberately, slowly. Because slow storms do not just look more dangerous on a satellite loop, they are more dangerous. A slow storm lingers over the same patch of ocean, drawing heat upward continuously. A slow storm drops its rain on the same soil hour after hour until the ground cannot absorb a single additional drop. A slow storm grinds its winds against the same structures, the same trees, the same power lines, not for 4 hours but for 12, for 18, for longer than anything was designed to withstand. The forecast models have arrived at a consensus. Sinlaku will intensify. Not gradually, not politely. Within the next 72 to 96 hours, this system is projected to explosively deepen from where it stands now into a Category 3 or Category 4 equivalent, sustained winds of 130 miles per hour or higher. Some model runs are gesturing toward Category 5. That is not a fringe forecast from a single outlier. That is the scientific center of gravity of the current guidance. The only open question is how strong it gets before landfall, and whether the margin of error breaks in favor of the 170,000 people who will still be standing on that island when it arrives. And the destination is already decided. Guam, the Commonwealth of the Northern Mariana Islands, United States territory. 212 square miles of volcanic and limestone rock sitting in the middle of the warmest stretch of ocean on Earth. When most Americans hear the phrase hurricane hitting U.S. soil, they think Florida. They picture the evacuation contraflow on I-75, the caravans of cars heading north, the hotels filling up in Atlanta and Nashville. They picture a system, imperfect but functional, that gives people a way out. Guam does not have that system. Guam does not have a way out. There are no highways pointing inland because there is no inland. There is one airport, Antonio B. 1 Pat International, serving the entire island. One airfield. If its runways crack, if its terminal floods, if its fuel supply is compromised, there is not a second airport 3 hours up the road. There is nothing up the road. The road ends at the ocean. There is one hospital. Guam Memorial Hospital, one facility for 170,000 people. One electrical grid. Not one grid per municipality, one grid total. When it fails, everything that depends on it fails. The water treatment plants, the pumping stations, the refrigeration units and pharmacies, the ventilators in the ICU. There is no neighboring grid to borrow from. There is no mutual aid agreement with a utility 2 counties over. There is only this island and whatever is still standing when the storm is done. The military dimension of this is not incidental. It is the reason the world is watching even when mainstream coverage has moved on to the tornado forecasts in Oklahoma. Andersen Air Force Base on the island's northeastern side is not a regional outpost. It is the forward spine of U.S. air power in the entire Indo-Pacific. Rotating deployments of B-52 Stratofortresses, B-1B Lancers, and B-2 Spirit bombers operate from Andersen. Aerial refueling tankers extend their reach across the Pacific. If Andersen goes offline, if its runways are fractured, if its fuel infrastructure is compromised, if its air traffic control systems are destroyed, the deterrent posture the United States has spent decades projecting into the Western Pacific degrades in real time. Naval Base Guam carries nuclear-powered fast attack submarines. It is the only submarine maintenance and refit facility in the entire Western Pacific. If the floating dry docks fail, if the fuel systems are breached, if the logistics chain is severed, those submarines cannot be serviced. There is no backup facility. There is no alternative port. The submarine capacity of the U.S. Pacific Fleet is constrained by what happens on this island in the next 3 days. The bombers will redeploy. The aircraft will fly out ahead of the storm. The submarines will submerge into deeper water where the typhoon cannot reach them. But the 20,000 military personnel and their families, the spouses, the children, the parents who came here because their son or daughter was stationed here, they will stay. They are residents. They have leases. Their children are in school. Some of them have been trying to transfer out for months. The storm arrives in 3 days. The government of Guam issued a state of emergency on April 9th. Typhoon watches are active for Guam, Rota, Tinian, and Saipan. Typhoon Condition of Readiness 3 has been declared across the Commonwealth of the Northern Mariana Islands, meaning destructive winds are now considered possible within 48 hours. The airport is restricting flights. Hospitals are canceling elective procedures. Supply ships and cargo planes are making their final runs before the window closes. The National Weather Service has posted a flood watch calling for 15 to 20 inches of rainfall. 15 to 20 inches on a 212 square mile island is not neighborhood flooding. That is island-wide inundation. That is storm surge pushing salt water into the municipal water supply. That is the drainage infrastructure simply giving up, unable to move water fast enough, backing it up across roads, into homes, into shelters. When you see that number from the mainland, it blurs into abstraction. But imagine you are a parent in Dead Ito, Guam's largest community, listening to the wind start to build against your concrete walls. Imagine you are a nurse at Guam Memorial Hospital knowing that the backup generators are aging and the roof has soft spots and you cannot leave your shift because the hospital cannot close. Imagine you are a teacher who survived Typhoon Mawar in 2023, who watched 4,600 structures destroyed, who watched the power stay off for weeks, who watched 80% of the island lose running water, and now you are being told to prepare for something potentially worse. In 3 days. Sinlaku is the first typhoon of the 2026 Western Pacific season to directly threaten U.S. territory. And the 170,000 people in its path are not evacuating. They will shelter in place. They will ride it out. And when the sustained winds exceed 90 miles per hour and the debris starts flying and the cell towers go silent, there will be no leaving. Not by choice. By physics. By geography. By the simple, unalterable fact of living on a 212 square mile island in the middle of the Pacific Ocean. That is Sinlaku's catastrophe. But Sinlaku is not the whole story. Sinlaku is happening inside a broader atmospheric collapse. One that is simultaneously pulling every available disaster response resource on the continental United States in 6 different directions. That is the compound pileup. And that is where the real catastrophe lives. 3 years ago, almost exactly 3 years ago, Guam absorbed Typhoon Mawar. May 24, 2023. Category 4 at landfall. Sustained winds of 150 miles per hour. The island had perhaps 5 to 12 hours of usable warning time before conditions made movement impossible. The damage, $3.3 billion by NOAA's conservative accounting. Over 4,600 structures destroyed or severely damaged. Not 4,600 homes, but 4,600 buildings. Residences, businesses, schools, clinics, government facilities, warehouses. The entire island lost power. Not a district. Not an outer neighborhood. Every single block, every community, every corner of the island went dark. The grid was gone for weeks. In some areas, power did not fully stabilize for more than 5 months. 80% of Guam's population lost water service. The water treatment plants, which depend entirely on electricity to function, went offline. 8 out of 10 families on a tropical island, an island surrounded by ocean, had no access to safe drinking water for weeks after the storm. The disaster was severe enough to trigger a presidential major disaster declaration. Mawar was the strongest typhoon to hit Guam since Pongsona in 2002. 20 years separated two Category 4 systems striking the same island. The infrastructure was designed around that spacing. The assumption that if a catastrophic storm hit, you would have a generation of recovery time before the next one. That assumption has now been invalidated. The recurrence interval that Guam's power grid, hospital system, housing stock, and transportation network were all engineered to accommodate is roughly one major hit per decade. Mawar broke that rhythm. And now, just 36 months later, Sinlaku is aimed at the same coordinates. An island that has spent 3 years trying to recover from one Category 4 typhoon is about to be asked to absorb another. The blue tarps still covering rooftops from Mawar repairs will be stripped away. The newly rebuilt structures will face the wind again. The grid that has been painstakingly restored will be tested again. The families that have slowly, painfully stabilized will be knocked backward again. The science behind Sinlaku's intensification is what separates this from a routine forecast. Rapid intensification, formally defined as a wind speed increase of at least 35 miles per hour within 24 hours, can happen far faster than that definition allows. Hurricane Otis in 2023 underwent intensification so extreme that meteorologists had to reach for new language to describe it. Its central pressure dropped 80 millibars in 18 hours. The previous record was 64. Otis went from tropical storm to Category 5 in approximately 12 hours. 12 hours. When it hit Acapulco, the city was completely unprepared. The death toll reached hundreds. Entire neighborhoods remain abandoned. Sinlaku is forecast to travel from Category 1 to Category 3 or 4 in just 72 to 96 hours. That trajectory is being enabled by sea surface temperatures in the western Pacific warm pool that are running 28 to 29 degrees Celsius, bath water warm, a heat reservoir the storm can draw from indefinitely. Vertical wind shear is low, meaning the upper atmosphere is not tearing the system apart. Upper ocean heat content is extraordinarily high, providing a deep energy supply. Low shear plus deep heat equals an explosive deepening environment. And Sinlaku's glacial forward speed amplifies all of it. A storm moving at 5 miles per hour does not ventilate itself the way a faster moving system might. It does not mix up cooler water from depth. It stays organized, concentrated, and dangerous for longer. The engine keeps running. The heat keeps feeding upward. The damage window stretches from hours into days. The truly lethal dimension of rapid intensification is what it does to preparation timelines. A forecast that shows a Category 1 system 36 hours out can become a Category 3 system 18 hours out. The decision you made yesterday, based on what the forecast showed yesterday, may now be a death trap. On an island where there is nowhere to evacuate to in the first place, that compression is not just dangerous. It is absolute. The ghost of Mawar is not a metaphor. It is 3 years of incomplete recovery, still visible in unrepaired rooftops and strained hospital systems and families who are still financially recovering, being asked to brace for a second blow. And it is happening inside an atmosphere that is producing catastrophe-scale events across the entire continental United States at the exact same moment. As of April 11, 2026, the National Weather Service has 234 active alerts posted across the continental United States. 234. That number is not a typical spring week. That is an atmosphere operating in a state of profound, fragmented instability, producing hazards so diverse and so simultaneous that no single meteorological mechanism explains them. You cannot point to one jet stream, one pressure system, one moisture plume and say this is causing everything. Because it is not. The atmosphere is fractured. 6 separate disaster-scale events are unfolding at the same time in 6 different regions, driven by 6 different atmospheric mechanisms, all converging on the same 48 to 72-hour window. Guam faces a rapidly intensifying typhoon threatening Category 4 landfall within 100 hours. The Great Plains from Oklahoma to Missouri sits under a severe thunderstorm and tornado watch. The Sierra Nevada from California into Nevada is under a blizzard warning with 10 to 30 inches of snow forecast above 7,000 feet, accompanied by sustained winds of 55 miles per hour. Kansas is under a flash flood watch, 4 to 5 inches of rain forecast to fall on soil that is already saturated from weeks of prior precipitation. Hawaii is under an all-islands flood watch driven by a completely separate tropical moisture feed, a different depression, spinning independently south of the islands, pushing warm moist air northward with no connection to Sinlaku whatsoever. And the Southwest, southern Colorado, Arizona, parts of New Mexico, is under a fire weather emergency with relative humidity forecast to drop to 8 to 14%, surface winds gusting to 35 miles per hour. 6 distinct hazard mechanisms. Each one serious enough on its own to command emergency management resources. All of them active simultaneously. This pattern sounds familiar, it should. In the first 5 days of April, a compound event merged 6 concurrent hazard categories across 5 U.S. regions. A few days later, April 8th through 9th, another compound sequence with similar diversity and reach. A pattern was taking shape. Now, barely into the second week of April, that pattern is delivering its third major compound event in 11 days. This is not random variation. This is not a statistical coincidence. This is a persistently amplified atmospheric state that is refusing to cycle back to normal. The jet stream is locked. The ridge over the western United States is pumping warm air northward without pause. The trough over the central United States is pulling cold air southward with the same relentlessness. The pattern is not resetting. It is not moving. And as it persists, it keeps manufacturing extreme events on top of extreme events. The Sierra Nevada blizzard is dropping heavy, wet spring snow above 7,000 feet in mid-April, with wind gusts approaching 40-year records for that elevation in that calendar month. Roads will close within hours. Travelers will be stranded. Power will go out across mountain communities. Kansas is facing 4 to 5 inches of rain on already saturated ground. The soil is at capacity. Water runs off immediately. Creeks become rivers. Arroyos become torrents. Vehicles stall in crossings that look passable but are not. Hawaii, seemingly distant from all of this, is experiencing its own separate moisture crisis. An independent tropical depression feeding warm, wet air northward across all major islands simultaneously. Volcanic terrain does not drain. Water runs off hard surfaces and floods immediately. The southwestern fire weather emergency stretches across 3 states. Relative humidity in single digits. Winds gusting past 35 miles per hour. If ignition happens, and in Arizona and Colorado in April, ignition happens regularly from agricultural burning, from vehicles, from equipment, fire spread becomes nearly unstoppable within minutes. Entire communities can be ordered to evacuate within hours. And all of this, every single element, is competing for the same pool of national response resources. The same National Guard helicopters. The same FEMA coordinators. The same hospital surge capacity. The same media airtime. The same public attention. And the place that loses in that competition, the place that gets buried beneath the noise of 6 simultaneous mainland disasters, is Guam. An island of 170,000 people waiting for a potential Category 4 typhoon while the continental United States stares in 6 other directions. While Guam is boarding windows and stockpiling water for a potentially catastrophic typhoon, something is activating across more than 2,000 miles of mainland America. The Storm Prediction Center has issued a slight risk for Saturday, April 11th, across the southern high plains. This is not one storm system. This is the opening sequence of a multi-day outbreak that will operate simultaneously with Sinlaku's assault on Guam, demanding forecaster attention, emergency resources, and response coordination from a system that is already stretched across 6 other active disasters. The setup is deceptively simple on the surface. Thunderstorm development is expected mid to late afternoon Saturday across southwest Texas and eastern New Mexico, fed by Gulf moisture pushing inland as daytime heating intensifies atmospheric instability. But the Storm Prediction Center has identified 30 to 40 knot deep layer wind shear, wind speed increasing dramatically with altitude, which will organize individual thunderstorms into something far more dangerous than isolated cells. These storms will merge into squall lines. And when that happens, the entire wind signature transforms. Gusts stop coming from vertical motion and start coming from the cold pool of rain-chilled air spreading outward at 50 to 60 miles per hour across everything in the system's path. But that is only the opening act. The true escalation is happening northeast, where an 850 millibar wind analysis shows winds forecast to strengthen from 40 knots to 60 knots by Saturday evening. This is the critical ingredient, the low-level jet. Horizontal wind shear at mid-levels is precisely what a rising column of air encounters as it climbs. The updraft tilts that horizontal shear into vertical rotation. That rotation intensifies. That rotation becomes a mesocyclone. And mesocyclones become tornadoes. The Storm Prediction Center is simultaneously tracking a warm front positioned across the middle and lower Missouri Valley, exactly where this wind shear is maximizing and moisture is richest. That convergence zone is where rotating supercells form with mechanical precision. That is where tornadoes happen. The models are calculating mixed-layer CAPE values, convective available potential energy, reaching 2,500 joules per kilogram across the outbreak zone. A typical spring severe weather day operates in the 500 to 1,500 range. The atmosphere on Monday will be roughly twice as late summer severe weather events, not mid-April. When you combine extreme moisture with extreme lapse rates, CAPE values in some locations exceed 3,000. The dry line, that invisible boundary separating absolutely bone-dry air to the west from moisture-laden air to the east, will support the most dangerous storm type the Storm Prediction Center recognizes: dryline supercells. These produce the largest hail, the most powerful updrafts, the tornadoes that rotate with mechanical precision because the wind shear is oriented perfectly to convert horizontal spin into vertical rotation. The tornado probability contours are no longer showing isolated risk. They are showing a corridor of meaningful tornado potential across Oklahoma and Kansas, with a 10 to 15% probability of significant tornadoes within 25 miles of any given point in that corridor. Monday and Tuesday, the pattern locks in completely. The Weather Prediction Center has issued an increasingly active pattern statement. Language that in operational meteorology means high confidence, not uncertainty. A persistent mid-level southwesterly flow means storm steering winds will not change. Storms will not race northeast and weaken. They will maintain their trajectory and intensity because the upper-level pattern is frozen. The models are tracking a double-barrel low-pressure system, two separate low-pressure areas approaching sequentially from the west and northwest, passing through the region over a 72-hour window. The first brings the most severe weather. The second extends the threat northward. Dew points in the 60s reaching as far north as Minneapolis by Tuesday. Minneapolis. In mid-April. EF2 tornadoes produce winds of 111 to 135 miles per hour. They strip roofs from frame houses completely. They overturn mobile homes. They snap mature trees. A track 100 yards wide and 10 miles long destroys 250 acres of terrain and puts neighborhoods on a years-long rebuilding timeline. EF3 tornadoes produce winds of 136 to 165 miles per hour. They take brick structures from the roof to the foundation. They debark trees. They move heavy vehicles multiple blocks. The forecast wind shear and CAPE environment is consistent with EF3 production, and possibly EF4 if supercells maintain organization over the Texas-Oklahoma corridor. Over 100 million people live within the threat zone. Dallas, Oklahoma City, Kansas City, Wichita, Des Moines, St. Louis. These are not rural counties. These are metropolitan centers with hospitals and schools and populations that will require search and rescue, shelter coordination, and emergency management surge capacity that simply does not exist to cover a multi-day, multi-state outbreak. And here is where the central thread pulls tight again. Every tornado warning issued in Oklahoma is an emergency manager not looking at Guam. Every rescue helicopter dispatched to a Kansas flood zone is not available for Guam. Every FEMA coordinator running shelter logistics in Missouri is not running supply logistics for an island that is about to lose its power grid and its water system simultaneously. The compound pileup is not just in the atmosphere. It is in the response system itself. What is happening across the country right now should seem impossible. And yet it is the actual operational picture. Red flag warnings and fire weather watches are active across the Southwest and High Plains, relative humidity collapsing to 8 to 14%, surface winds gusting past 35 miles per hour. At the exact same moment, winter storm warnings are posted for the Sierra Nevada, with blizzard conditions forecast to drop 10 to 30 inches of snow above 7,000 feet. Fire danger and single-digit humidity existing within the same nation-state as 2,500 joule CAPE environments building thunderstorms and flash flooding in the plains. This is not a forecast error. This is not model inconsistency. This is the atmosphere finding a way to produce contradictory hazards simultaneously, fire and blizzard, drought and deluge, because the pattern driving it is capable of sustaining both at once. The National Weather Service office in Rapid City has issued a critical fire weather alert for northeastern Wyoming and southwestern South Dakota. Winds forecast at 18 to 25 miles per hour sustained, gusting to 35 to 40. Relative humidity dropping to 8 to 14%. In those conditions, grass becomes tinder that does not wait for a match. A fire starting at 2 in the afternoon can consume 5,000 acres by sunset. Suppression becomes nearly impossible above certain wind thresholds. Ground crews cannot outpace running fire moving faster than a person can jog. Water trucks cannot keep up. Tucson's National Weather Service office has issued a red flag warning for southern Arizona. Same wind speeds. Same catastrophic humidity range. The bunch grasses of the shortgrass and mixedgrass prairie that dominate the high plains, once dried below 4% moisture content and sustained 8% relative humidity and winds above 20 miles per hour, burn with essentially no suppression capability. The fire behavior transitions to running ground fire. Across Kansas, Colorado, and Nebraska, fire weather watches are in effect. 7 watches. 4 red flag warnings. The Storm Prediction Center has flagged dry thunderstorm risk for Saturday, elevated atmospheric lightning with rain that evaporates before reaching the ground, leaving behind ignition points in an environment where suppression will be nearly impossible. And the March heat wave is not background noise here. 6 weeks ago, 16 red flag warnings were issued across 9 states with humidity values as low as 8%. The National Interagency Fire Center flagged at the time that those values were not typical for March. The soil moisture deficits from that event have not recovered. Spring precipitation has not been sufficient. The baseline fire danger established in March is still present. The vegetation still primed, the ground still dry, and now in mid-April, the same atmospheric configuration is reasserting itself with greater intensity. On the western side of the Continental Divide, the Pacific low-pressure system is delivering something entirely different. The Sierra Nevada is under a winter storm warning. Central Sierra, including Yosemite Valley, Kings Canyon, and Sequoia National Parks, is in the warning zone. 10 to 30 inches of snow above 7,000 feet. Gusts exceeding 55 miles per hour. Whiteout conditions. Visibility below 1/4 mile. This is April blizzard snow, not dry powder from a Canadian air mass but heavy, wet spring accumulation that will melt rapidly and violently once it transitions to rain at lower elevations, loading river systems that feed California's water infrastructure ahead of the spring melt season. In Yosemite Valley itself, at 4,000 feet, the precipitation will fall as heavy rain. Saturated ground and rapid high country runoff will combine to create flash flood risk in the major waterfall corridors. Bridal Veil Creek, Yosemite Creek, and the Merced River are forecast to exceed bank full stage. Park emergency rescue capacity in a major April storm is severely limited. Helicopter rescue is not possible in whiteout conditions. People caught in the high country may be sheltering in place for 36 hours or longer. The dry line is the physical boundary where all of this paradox meets. To its west, dry continental air masses pushing northward at accelerating speeds. Relative humidity in single digits. Fire ignition temperatures dropping towards spontaneous combustion thresholds. To its east, Gulf moisture surging northward. Dew points climbing into the 60s. Cape values building toward 2,500 and beyond. Severe thunderstorm risk maximizing. The dry line is the boundary between these two worlds. A real, physical gradient where temperature shifts rapidly, wind direction reverses, and relative humidity jumps from 5% to 65% across a distance of a few miles. And it is positioned exactly where jet stream amplification is strongest. A single atmospheric structure producing contradictory hazards across different regions in the same 48-hour window. The fire threat and the flood threat are connected. They are twin manifestations of the same underlying moisture pattern. Drought on one side of the dry line, surplus on the other, created by the same jet stream structure. They are separated by 300 miles. And both of them are happening while Sinlaku consolidates its power in the Pacific, fed by the same atmospheric engine amplifying the jet stream across North America. The convergence of 6 separate hazard categories, Category 4 typhoon intensification, severe weather outbreak, tornado potential, fire weather emergency, blizzard conditions and flash flood risk, is not a coincidence. But it is also not a single unified cause. It is the intersection of multiple atmospheric drivers arriving at maximum intensity in the same calendar week. The first piece is ENSO, El Niño Southern Oscillation. The oceanic Niño index has risen from -0.55 in the October through December period of 2025 to -0.16 in January through March of 2026. A rapid transition. The atmosphere is moving from the tail end of a La Niña pattern, which favors cool, wet conditions in the Pacific Northwest and warm, dry conditions in the Southwest, toward a neutral state. The Climate Prediction Center currently puts a 62% probability on El Niño conditions developing by the June through August window of 2026. During ENSO transitions, The subtropical jet stream becomes anomalously amplified. Troughs deepen. Ridges strengthen. Temperature and moisture gradients become more extreme. The jet stream, that river of air flowing around the planet at 35,000 feet, changes its geometry, meandering more dramatically, holding its patterns longer, impacting larger regions. Think of it like a bathtub. Under normal conditions, the water sloshes gently. During an ENSO transition, the sloshing becomes exaggerated. The water piles up deeper on one side, pulls back further on the other. The oscillation becomes more extreme. The Pacific warm pool, near the equator where ocean temperatures exceed 85 degrees Fahrenheit, is the deep water side of the Pacific bathtub. When an ENSO transition amplifies the jet stream, it also changes how that heat is distributed, including how far north and south it influences the energy available to tropical cyclones. The Western Pacific warm pool is where Sinlaku is intensifying right now. Sea surface temperatures of 28 to 29 degrees Celsius, 82 to 84 degrees Fahrenheit, sustained across the region where the typhoon is feeding. The difference between 28 degrees and 30 degrees Celsius is, in tropical cyclone terms, the difference between a Category 2 and a Category 4. ENSO transitions may be slightly enhancing the warm pool's heat content. We are in the ramp phase. The energy signatures that precede El Niño onset include above-average heat content in the tropical Pacific. Rapid intensification events in the Western Pacific tend to cluster during these phases. This is why Sinlaku is not separate from the mainland disaster. The same ENSO transition that is amplifying the subtropical jet stream is also enhancing the Western Pacific warm pool and enabling a tropical cyclone to achieve major hurricane intensity. The same atmospheric engine is running both stories simultaneously. The jet stream amplification driving the mainland events is, in technical terms, Rossby wave amplification. The atmospheric pattern is oscillating more strongly. A trough positioned over the western United States creates a ridge over the eastern United States. That ridge pulls Gulf moisture northward. The moisture meets the trough's leading edge and creates the massive instability gradients feeding supercells. On the western side of the same trough, in the dry continental air pulled backward as the system approaches, fire danger maximizes. The Sierra Nevada sits directly in the trough's moisture path, receiving the heaviest precipitation on its western flank. On the eastern side of the continent, the ridge creates subsidence, downward motion that warms the air compressionally and locks the high-pressure fire danger pattern into place. Warm, sinking, dry air suppresses clouds, creates clear skies, allows rapid surface heating, and sustains maximum fire danger. This is one atmospheric structure producing multiple contradictory hazards across multiple regions simultaneously. The truly frightening dimension is the trajectory. If the Climate Prediction Center's 62% El Niño probability holds, and if European Center for Medium-Range Weather forecasts ensemble members showing super El Niño conditions, plus 2 to 3 degrees above the 20-year average, verify in the months ahead, then the jet stream amplification we are watching right now is not the peak. The troughs will deepen further. The ridges will strengthen further. Cape values will climb toward 4,000. Fire weather threats will become more frequent. Severe weather outbreaks will become more persistent. What we are watching in April is potentially the warm-up act for May, June, and July. The disaster unfolding on Guam is not happening in isolation. While Typhoon Sinlaku charges across the Western Pacific, the space above it is telling its own parallel crisis story, one that is actively making communication and coordination more difficult at precisely the moment when flawless coordination might mean the difference between an organized response and a desperate one. The atmosphere does not operate in a vacuum. The systems built to monitor it are not insulated from what happens in the layers above. Right now, today, April 11, 2026, the Space Weather Prediction Center is forecasting G1 minor geomagnetic storm conditions. The solar wind, a continuous stream of charged particles flowing outward from the sun at approximately 400 kilometers per second, is pushing harder than usual against Earth's magnetosphere. The trigger is a positive polarity coronal hole high-speed stream that departed the solar surface days ago and has now arrived, like a delayed message from the sun. The KP index, the standard measure of geomagnetic disturbance on a scale from 0 to 9, is forecast to reach 4.67. Just below the threshold for a full geomagnetic storm classification, but elevated enough to matter in ways that most people never see. A KP of 3 is routine. A KP of 4 is where effects become noticeable. A KP of 5 is where warnings go out to critical infrastructure operators. At 4.67, the effects are real but not yet catastrophic. Solar activity itself remains modest, only C-class flares from 6 active regions. But one number reveals the actual threat: the 2 mega-electron-volt electron flux, currently standing at 1,713 particle flux units, classified as high. 1,000 particle flux units is the threshold where real effects on satellite systems begin. We are well above that. And this elevation has persisted for 8 consecutive days. 8 days of accumulated stress on satellite electronics. 8 days of bit flip errors building up in communication systems. 8 days of gradual, cumulative degradation in the infrastructure that Guam depends on entirely. Guam's ability to coordinate emergency broadcasts, manage military logistics, track supply shipments, and navigate airlift operations depends completely on satellite infrastructure that is currently operating under degraded space weather conditions. The elevated electron flux does not knock satellites offline suddenly. It increases error rates in sensitive data streams. It adds noise to GPS signals that navigation systems depend on. It introduces subtle errors in the telemetry that emergency managers use to track personnel deployments and aircraft positions. When you are trying to coordinate the movement of 170,000 people in a 48-hour window, when you are broadcasting evacuation readiness instructions across an island where some communities have limited ground-based communication infrastructure, a KP of 4.67 is not a minor inconvenience. It is a direct compression of the safety margins the system depends on. Geostationary satellites, which orbit at a fixed point 36,000 kilometers above the equator and provide the relay infrastructure for emergency services, military coordination, and weather data transmission, are particularly vulnerable to the current electron flux. They cannot maneuver. They cannot seek shelter. They experience direct electron bombardment. Their solar panels degrade more quickly. Their onboard computers generate more errors. The military communication satellites relaying emergency orders to Guam's municipalities, experiencing this now. The NOAA satellites providing real-time weather imagery and intensity estimates for Sinlaku, operating in a noisier environment now. When you are trying to determine whether Sinlaku is a Category 3 or accelerating toward Category 4, you need precise wind measurements. You need satellite data you can trust. Right now, that data is arriving through a channel with more static. Less than 48 hours ago, the Artemis II crew splashed down in the Pacific Ocean after completing the farthest human journey from Earth in more than 50 years. Mission controllers at Johnson Space Center were actively managing the elevated electron environment during re-entry, calculating trajectory adjustments, accounting for potential communication delays. The crew returned safely. But the fact that Mission Control was tracking and managing space weather during that operation tells us something direct. High-energy space weather affects critical infrastructure in measurable, concrete ways. The environment that shaped Artemis II's return is the same environment affecting Guam's emergency response infrastructure right now, with considerably less prestige attached, and considerably less national attention focused on it. Additionally, 2 asteroid transits deserve their proportional place in this picture. Asteroid 2026 GR1 passed within 0.85 lunar distances, inside the space the Moon typically occupies, without incident. Asteroid 2013 GM3 will make a sublunar approach of 0.68 lunar distances on April 14, roughly coinciding with Sinlaku's peak impact window. These objects do not affect weather. Asteroids cannot steer typhoons or amplify wind speeds. But they are evidence of a solar system that is, right now, in a moment of elevated concurrent activity. The space environment is amplified. The solar wind is stronger. The electron flux is elevated. The asteroid transits are happening. The region of space in which we live, from the atmosphere's surface to the edge of near-Earth space, is experiencing a moment of simultaneous heightened motion. 48 hours before Sinlaku became the lead story in every Pacific weather briefing room, before TCC timelines started compressing, before the Space Weather Prediction Center issued its alerts, something remarkable happened in the Pacific Ocean. The Artemis II spacecraft, carrying 4 astronauts, splashed down safely. The mission had sent human beings to a distance of 252,756 miles from Earth, beyond the Moon's orbit, into regions of space where no human had traveled in more than half a century, and returned them precisely to a designated splash zone in the Pacific. They did it in a country that cannot evacuate 170,000 of its own citizens from a 212-square-mile island sitting in the path of a Category 4 typhoon. They did it while those citizens were boarding up windows and rationing water and praying that their concrete roofs would hold. The United States demonstrated the capacity to navigate life support systems, maintain real-time communication, and execute precision re-entry across a 250,000-mile journey through an environment we do not fully understand. At the exact same moment, it cannot provide evacuation for the residents of Guam because there is nowhere to evacuate to. One airport, one hospital with limited surge capacity, one power grid, one island, alone in the Pacific 2,500 miles from the nearest major U.S. mainland utility. When Typhoon Mawar destroyed Guam's electrical grid in 2023, there was no neighboring utility to draw from. The island went dark for weeks. Hospitals ran generators that consumed fuel at desperate rates. Water systems failed. Some areas waited more than 5 months for stable power. Now that same grid, rebuilt at enormous cost, still not fully restored in some stretches, faces its second Category 4 test. The psychological experience of sheltering in place on Guam is fundamentally different from hurricane preparation on the mainland. In Florida or Louisiana, evacuation is a choice. Difficult, expensive, exhausting, but available. You join the contraflow on the interstate. You drive north. You have family in Georgia. You find a hotel room in Tennessee. On Guam, you pick the strongest concrete building you can find. You tape the windows. You stack the bottled water. You check the backup radio batteries. And you wait. The TCC system provides Guam's escalating framework. TCC-5 for early monitoring, TCC-4 for emerging concerns, TCC-3 for the threat becoming clear, school closures, business reductions. TCC-2 for the 72-hour impact window, when the island begins full shelter-in-place posture. TCC-1 for the final state, full lockdown, everyone in secure shelter. The government wants to move from TCC-3 to TCC-1 within 48 hours. But as Typhoon Otis demonstrated in 2023, going from tropical depression to Category 4 in less than 96 hours, that timeline can collapse in a single forecast cycle. If Sinlaku outpaces its forecast the way Otis fragmented, forecaster bandwidth is divided. Everyone with expertise is being pulled in 7 directions. If Sinlaku outpaces its forecast in this window, the full and undivided attention of a nation that is simultaneously managing a multi-state tornado outbreak affecting over 100 million people, coordinating blizzard response in the Sierra Nevada, managing flash flooding from Kansas to Hawaii, and fighting fire weather emergencies across 3 western states will not be available. Guam will be one of several active disasters competing for the same limited resources and attention at the exact moment every resource and every unit of attention matters most. The typhoon does not slow down while the mainland crisis unfolds. It does not check the news. It does what the atmospheric conditions allow. And those conditions are currently favorable for rapid intensification. As with every major typhoon that threatens U.S. territory, a particular kind of narrative will surface from online forums and alternative media channels. The storm is not a product of ordinary atmospheric physics, the theory goes, but a deliberate event, steered, intensified, manufactured by human technology. Weather modification theories have circulated since the dawn of modern meteorology. In the current climate of institutional distrust and instant information distribution, they have particular traction. The most common version centers on HARP, the High-Frequency Active Auroral Research Program facility in Gacona, Alaska. The theory, HARP transmits high-frequency radio waves into the ionosphere, which somehow energizes or steers weather systems toward targets. It deserves a direct, physics-based answer, not just dismissal. Here is that answer. HARP operates in the ionosphere, approximately 100 kilometers above Earth's surface. A typhoon develops in the troposphere, the lowest 12 kilometers of atmosphere where weather actually happens. These are separate physical regions with distinct mechanisms. HARP has no direct mechanical connection to tropospheric systems and no known physical pathway to influence them. The energy budget of a Category 4 typhoon runs approximately 5 exajoules per day. 1 exajoule is 1 followed by 18 zeros in joules. 5 exajoules per day is roughly equivalent to the total energy consumption of all human civilization globally over the same 24-hour period. HARP's peak transmitted power output is approximately 3.6 megawatts, 3,600 times more powerful than a household microwave oven. You could run your microwave continuously for an entire year and not heat the Pacific Ocean by a single degree. The scale difference between HARP's capabilities and a Category 4 typhoon is not a matter of efficiency. It is a difference of fundamental category. To artificially create or steer a system of Sinlaku's magnitude would require technology that does not exist, could not exist within currently understood physics, and would be transparently visible to hundreds of scientists and satellites monitoring the system in real time. HARP is a real facility doing real ionospheric science. It is not weather control. The gap between its actual capabilities and the theories about it is the gap between reality and fiction. But here is what is more interesting. The impulse to search for a human explanation for Sinlaku is not entirely irrational. Because humans are involved in the conditions that created it, just not through HARP. The warm pool feeding Sinlaku is running 2 to 3 degrees above historical norms because of global greenhouse gas emissions accumulated over 2 centuries. The excess heat in the Western Pacific is there because we put it there through fossil fuel combustion, industrial emissions, and 200 years of decisions about how to power human civilization. The jet stream pushing Sinlaku toward Guam is partly amplified by the altered temperature gradient between the Arctic and mid-latitudes, a gradient disrupted by differential warming in the polar regions. The real human fingerprint is not in any transmitter array. It is in the foundational conditions of the ocean and atmosphere. We made this system warmer. We made it more hospitable to rapid intensification. We made it more likely that a storm arriving at Guam would arrive as a Category 4 rather than a Category 2. That is a human responsibility of an entirely different order. The climate science is careful here. We have moderate confidence that climate change is increasing the proportion of tropical cyclones reaching major intensity. We have strong confidence that warmer sea surface temperatures are expanding the regions where rapid intensification is physically possible. The cluster of extreme rapid intensification events, Hurricane Patricia in 2015, Hurricane Michael in 2018, Hurricane Otis in 2023, and potentially Typhoon Sinlaku now, is precisely what climate models have long predicted should become more common. A single storm cannot be attributed to climate change with certainty. The broader trend can be. The science standing on its own is alarming enough. The ENSO transition is creating favorable conditions. The warm pool is supplying the fuel. The jet stream amplification is steering Sinlaku toward territory that cannot evacuate. The compound pattern of 6 simultaneous mainland events is fracturing national response capacity. The space weather overlay is degrading satellite communications at the worst possible moment. None of this requires a hidden explanation. The physics is the explanation, and it is quite dire enough on its own. Now we return to the question the title posed. A Category 4 typhoon is about to hit U.S. soil. And that is not even the worst part. We have traced the details. We have examined the space weather. We have noted the cruel irony of Artemis II. We have walked through the atmospheric science. Now the answer. What is the worst part? The worst part is not Sinlaku. The worst part is not the mainland tornado outbreak or the Sierra blizzard or the fire weather emergencies or the flooding in Kansas and Hawaii. The worst part is what all of these things reveal when they arrive simultaneously and what that reveals about the world we are now entering. Typhoon Sinlaku as a standalone event is already a major disaster. A Category 4 typhoon striking Guam, an island of 170,000 people with no evacuation route, would dominate the news for weeks. The damage would be staggering. The recovery would take months. The rebuilding would take years. People would die because that is what happens when 130-mile-per-hour winds meet human structures. But Sinlaku is not striking in a moment of national calm. It is striking while the continental United States is simultaneously managing a multi-day tornado outbreak affecting more than 100 million people across the Great Plains. It is striking while a blizzard is threatening to cut off mountain communities in the Sierra Nevada. It is striking while flash flooding threatens Kansas, while Hawaii is under flood watches, while fire weather emergencies are active across 3 western states, and while the upper Midwest is dealing with its own rain-on-snow conditions. 7 distinct disasters. 7 distinct resource demands. 7 separate emergencies, all competing for the same FEMA teams, the same air transport assets, the same emergency medical personnel, the same media coverage, the same forecaster attention. The first consequence is delay. When Guam needs confirmation that national assets are being prepositioned, the answer may not arrive for hours, because the operations center is simultaneously managing tornado briefings in Oklahoma, flood coordination in Kansas, blizzard response in California. When emergency supplies need to be airlifted, the military transport that could have arrived in hours may be diverted to a fire zone. When coordination signals need to go out, they are queued behind other signals. These delays are not dramatic. They are normal friction in a system stretched across simultaneous crises. But in a place where the preparation window is 48 hours and can collapse to 12, normal friction becomes catastrophic. The second layer is the rapid intensification timeline. The forecast calls for Sinlaku to reach Category 3 or 4 status within 72 to 96 hours. but rapid intensification events outpaced their forecasts. Hurricane Otis intensified from Category 1 to Category 5 in 24 hours, a shift that most forecast models failed to predict until it was happening in real time. If Sinlaku follows the Otis pattern rather than the consensus, the 48-hour preparation window does not remain 48 hours. It collapses to 24. TCC3 becomes 12 hours from full lockdown. And 12 hours is not enough time to ensure 170,000 people, including the elderly, the disabled, those in remote villages, those in hospitals, are in secure positions with adequate supplies and information. Compound pileup plus rapid intensification means Guam is competing for resources while the window for those resources to matter is actively shrinking. The two pressures work against each other simultaneously. The compression accelerates. But the deepest pattern here is not about this week. This compound event is the third in 11 days. 11 days ago, the atmosphere produced a multi-billion-dollar tornado outbreak across multiple states. The following week brought another significant severe weather episode. Now the same amplified jet stream pattern is driving a multi-continent disaster sequence. This is not a 1 in 50 years event. This is a pattern. And the pattern is accelerating. The Climate Prediction Center's 62% El Niño probability, if it verifies, if equatorial Pacific temperatures rise to +2 or 3 degrees above the 20-year average, means the jet stream amplification driving these compound events will not peak in April. It will intensify through summer and fall. The Cape values will climb higher. The fire weather threats will become more frequent. The severe weather outbreaks will persist longer. What we are watching in April is potentially the beginning of a months-long intensification, not the peak. The truly unsettling question, the one that atmospheric scientists keep arriving at but cannot fully answer, is this what a changing climate actually looks like in practice? Not one singular superstorm that commands all national attention and marshals a unified response, but many moderate to severe events, arriving in such density and frequency that the emergency management system simply runs out of the bandwidth needed to handle all of them adequately. Is the real threat not any individual typhoon or tornado outbreak or blizzard, but the compound pileup itself? Enough simultaneous events that response cannot be focused, resources cannot be concentrated, preparation time cannot be guaranteed for every threatened population? Because that is what is happening right now. Guam cannot evacuate. Hawaii cannot turn off the tropical moisture feed. The Sierra Nevada cannot refuse the snow. Kansas cannot prevent the flooding. Each of these events is unfolding in the same country in the same 48-hour window, and they are competing for national attention not by coincidence, but because the atmospheric state is persistently amplified across the Pacific, North America, and the tropical Western Hemisphere simultaneously. The atmosphere is not doing one extraordinary thing. It is doing 6 ordinary things at the same time. And the compound pileup of 6 ordinary events is producing a cascading disaster that no single event could generate alone. The real catastrophe is not Sinlaku. The real catastrophe is everything else. The real catastrophe is the silence of a system not yet broken, but stretched to its limits, and the dawning understanding that this is not an anomaly. This is the new pattern. We are no longer in the age of the singular superstorm. We are in the age of everything simultaneously all the time. And the only way through it is by paying attention to every forecast update, every atmospheric shift, every moment when the questions we have been asking stop being theoretical and become real. That moment is already in motion. In the next 72 hours, we will learn whether the forecast holds or whether Sinlaku outpaces it. We will learn whether the mainland disaster threat deepens or dissipates. We will learn whether the space weather overlay degrades communication when it matters most. We will learn whether national response can pivot fast enough to matter for 170,000 people who cannot leave. Watch for the updates. Watch for the shifts. The atmosphere is doing 6 ordinary things at the same time. 170,000 people cannot evacuate. And we are about to find out what happens when those two facts collide.